Hey everyone, we are going to spend a few moments today pretty much reviewing graphing and a few ways that we can evaluate different sets of data. So to start off here, if we collect data and we want to make a graph, we're really going to be comparing two different variables, the independent variable and the dependent variable. If you remember, the independent variable, good start here. The independent variable is the variable that the experimenter is going to change. And that's always going to be graphed on the x-axis. The dependent variable is what's going to respond to changes in the independent variable. So it is the variable that changes as a result of changes made by the experimenter. And what that's referring to is the independent variable. There could be other circumstances or criteria that are changed, whether directly or indirectly, depending on the experiments, that could affect the dependent variable. Oftentimes those are considered error because we only want to change one variable, the independent variable, in any experiment. And the dependent variable gets graphed on the y-axis. And if you remember from a previous class with me, the acronym DRY mix, and what this stands for, DRY, we have dependent, and that responds, I kind of cram this in here, on the y-axis. Mix, this is manipulated. Independent variable, x-axis. Apologize if that's kind of smashed in there. Feel free to pause this, take a closer look at it, and make sure you understand what dry mix means. If you have another acronym to use, by all means, go for it. Any axis of a graph is going to be labeled with quantities and units. You would have heard me talk about this many times in years past for proper scale and labels on a graph. I've always said the safe way to title your graph, which you always need a title, is as the dependent variable versus the independent variable. This could be something like reaction rate versus time. Whatever your labels are on your X and your Y, combine them together versus each other, and there is your title almost every time in a nice, safe way. Line of best fit can be one of two things. It can be a straight line, or it could be a curved line. Whatever's going to best fit your data that you have, and rarely are they completely straight, but they can be. But it's going to approximate the relationship amongst a set of data points. Extrapolation, if you think about our Barbie doll bungee jumping lab, means to extend the line that goes beyond the region which data was taken. So if we collect data from points 1 through 10, and we try to extrapolate and figure out at point 12 what might our value be. So to review, the slope of a line is defined as the ratio of the change in y over the change in x for any 2 points on the line. So it is the change in y over the change in x, which is vertical change over horizontal change, which can also be considered change in the dependent variable over change in the independent variable. We'll take a look at a few different mathematical relationships here. The two most common ones that we see, so when two quantities are directly proportional, meaning when an increase in one variable will cause an increase in the other variable. So both are increasing together. We tend to see that on a graph as a linear line, increase on both the x and the y. Two quantities may be inversely proportional when an increase in one variable causes a decrease in the other. Two quantities may have a constant proportion if an increase in one does not cause a change in the other. And we tend to see that as a kind of a flat, stagnant line. Two quantities have a direct squared proportion if an increase in one causes a squared increase in the other. And we'll see this as a rapidly increasing line. And two quantities, the last one here, have a indirect squared proportion. If an increase in one causes a squared decrease in the other, and these look kind of similar, the direct squared and the indirect squared graphs. So it all depends on the relationship between the data that's going to help establish what type of relationship we have. And by looking at the numbers and evaluating the numbers, it gives us a better understanding of exactly what they mean. So a little review here on evaluating experimental results. Most of this you should have used before. We would have used a lot of this in chemistry if you had taken that with me. A form of data analysis looking at the range of measurements. What that is the difference between highest and lowest values in a given data set. So if we look at the data above there in the table, and we want to look at the range of measurements for average temperature, we'd find our lowest value, 10.2, and the highest value, which is 23.5. Subtracting those two, will give us the range of our measurements. The mean is known as the average. Value of a set of measurements. This can be represented with a somewhat complicated equation, which I'm not going to get into right now because we don't really use this in physics, so I'm not going to include this part here. The variance, which we won't really use too much either, but I want to give this to you here so you have it. The variance is the sum of the squares of the differences of the measurements from the mean divided by the number of measurements. Again, this can be represented with a pretty complicated equation here, which we're not really going to get into here. The standard deviation, which will be our third means of analyzing data, is the square root of the variance. Now what these four pieces here will allow us to do is to break down and analyze our data and use it to compare to other sets of data to see where similarities and differences might lie. So within a set of data, in a normal distribution, 68% of the data lies between x minus the standard deviation or x plus the standard deviation. It's our average x. And as we continue to extend out, 1 or 2 or 3 more standard deviations from the mean, 3 standard deviations plus or minus will get us a total of 99.5% of our data. Percent error has to do with measurements that are made during laboratory work, which may stand alone or be incorporated into one or more formulas to yield an experimental value. In some cases, may have been scientists, may have been somebody else, may come up with a probable value or what we call the accepted value. And this is what we need in order to calculate our percent error. For example, the density of iron may be accepted to be 8.4 grams per milliliter. If you measured this experimentally and got an average density of 8.2 grams per milliliter, we could compare these two and find the percent error between our experimental value and the accepted value. The difference between these is what we call the absolute error. And we can use this absolute error by dividing it by the accepted value and multiplying by 100 in order to get the percent error. So we divide the absolute error by the accepted value and multiply by 100. And in equation form, this is the absolute error divided by the accepted value times 100. This is probably the most common type of data analysis that we'll look at, is percent error, to give ourselves an idea of how far off we were from the norm or from that accepted value. So last of the new information from Unit 1. Bring any questions that you have into class tomorrow. Have a wonderful day.